What's going on, Kaylin? I got a question for you. How do you feel about vectors? SOHCAHTOA, breaking vectors into their components, all of that kind of stuff. Can you hear my voice? All right. It's a lot of work. I agree with you. It is work. It's a few extra steps that you have to take, and it's kind of a pain. But is it hard? Yes or no? Oh yeah, I agree. The really hard thing is going through all of the equations and then you find out that you missed the two. Or like what we did one day when we were recording was we missed a negative sign inside of the quadratic equation. It was supposed to be a positive sign and it was a negative sign or something like that. Yeah, I agree. The hard stuff is the really small stuff. Anyway, if you are a fan, or maybe you don't even need to be a fan, but if you can hang with um, with SOHCAHTOA, then this next chapter is going to be cake for you. And you're like, ooh, I like cake. It really is. It's actually going to be easier than projectile motion, for sure. Are we cool? And I figured what I need to do now is I should start you guys up on doing some of the the other chapters in physics. So I want to definitely get through as far as I can with talking about like the different aspects of physics. And so the first thing we're going to start off with is I'm going to start you guys off on chapter 5, which is called Newton's Laws of Motion. And you know how I always talk about physics? There's only going to be a few equations you learn. For this entire chapter, we are pretty much going to be using one equation. I'll tell it to you. You ready? And it's going to look incredibly easy. And you'll find out that it is incredibly easy. F equals ma. That's it. Just one. There's one equation to choose from. It's not 4 different equations. You have to figure out which one to use. There's one of them. That's it. Are we cool? Yeah, it is. It seems easy. It is not that bad. It gets a little bad when you're talking about two-dimensional motion, as we've seen happen in the past. And guess what? We have to introduce when we talk about two-dimensional motion, sine and cosine and tangent of theta. Yeah, we're gonna get into those kinds of things, and we're gonna go back to that thing where we say, if we put on our x direction glasses and only look at that component, this is what happens. And if we put on our y dimension glasses and we only look at that component, this is what happens. Um, I've taught civil engineering at Leeward Community College before, and you can spend an entire course on this equation. F equals ma. Literally. Seriously, I've taken courses. CE 381, I think it is. Civil Engineering 381. F equals ma. That's all we did. All we did, all day. F equals ma. We cool? So I can't say that it's like super easy because it can get very complicated and it will get very deep and all of that kind of stuff. But what I can say is, I don't know, it's kind of easy conceptually. All right, let me talk to you guys about what the different parts of this equation is. So this is Newton's second law, and what he's saying is F stands for force. Force is a measurement of how strong something is pushing or pulling, and it's measured in newtons. Why do you think it's measured in newtons? Because Newton was the dude who came up with this stuff. So we were like, let's honor Newton by calling it a Newton. If you make up something and it has its own special units, you can name it after you. This will be measured in kelvins or something like that. All right. M is your mass. Now, Europeans and most of the rest of the world measure it in kilograms. Are we cool with that? What does America measure mass in? Grams? No, no. Grams is simply kilograms, just 1,000th of a kilogram. No, America doesn't use grams. You don't go to the butcher shop and buy 300 grams of meat, do you? Ah, there we go. Pounds and ounces. Yes. Actually, you're 100% wrong. Totally wrong. And most people are like, what? No, in America we use pounds, right? No, no, no. Pounds is actually a measurement of force. It's not a measurement of mass. And that's a really confusing thing. And we'll get into that later on when we talk about what a weight is. But for those of you who are really curious, in terms of English units, a mass is actually called a slug. Yes, as in those creepy, slimy things that leave trails wherever they go out of their butt. That is the American version of mass. This is why a lot of people get confused, because when someone talks about a kilogram is not a measurement of weight, it's a measurement of mass. A newton is a measurement of weight or a force. A pound is actually a measurement of force. A slug is a measurement of mass in American version. Pretty crazy, huh? Bet you didn't know that. Blew your mind. I'll give you a second to pick your brain up off the floor. All right. Acceleration is measured pretty standard in meters per second squared. Are we cool? And of course, in American units, that's actually feet per second squared. Are we cool with that? But mass is actually so. I guess one of my points is that like the American way of measuring things is stupid. So in science, in every American physics class we teach, we don't even use American units. We pretty much stick with the scientific units. So why don't we do that? Force is measured in newtons, mass is measured in kilograms, acceleration is measured in meters per second squared. I will tell you if I'm using some kind of different convention, but for the most part, assume that we're using American rules. Are we cool? Now this equation kind of makes sense to me. Like I could probably derive this equation if I were as smart as Newton at his time. Actually, I don't even need to be as smart as Newton. Let's try to play with this equation a little bit. F equals ma. F over m equals a. Are we cool? So, let's see. Let's push. Kaylin, you have a son or a daughter? And if that's offensive for me to ask, don't. Yeah. Okay, you got a son, all right? And your son is what, like 1 year old? 16 months. All right, so one and a few months. All right. So we've got Kaylin pushing her 16th month old. I want to say a skateboard, but I know that you're a very responsible parent. So let's say a shopping cart. Okay, here's Kaylin pushing her 16th month old shopping cart. Are we cool? And Kaylin, it's just you and me here. But if this is this offensive to you, or like, are you ashamed of me talking about this, or is that all right? I don't know. I don't know why I thought. All right, okay, all right. So we got Kaylin pushing the 16-month-old inside of a shopping cart. All right, and then let's see. We've got Kaylin, or Kaylin's clone, pushing the 16-month-old who's inside of a Humvee. All right? And they want to have a race. They want to have the same acceleration. Okay? Now, what's the difference between the two scenarios? The weight, or more importantly, the mass, right? This one has a little mass, and this one has a big mass. Are we cool? So if I wanted to make these things, these accelerations equal, I would simply say, well, if I wanted to make these things equal, then I would say this needs a little force, and this needs a big force. Does that make sense? Or maybe we go like this. Maybe we approach it this way. Actually, I wasn't thinking about this correctly. That was correct analysis. But let's go with this. Say that we push both of these things with the same force. Okay, you push the Humvee with the same force you push the shopping cart. Okay. Now, if you're pushing with the same force, how do these numbers respond? Well, if you have over here, we have a force, and you're pushing it with a mass, a small mass, right? But you're going to be pushing with a big acceleration. Would you guys agree? Because it's a small mass, so you can accelerate it very quickly. Whereas, if the mass was really big, then your acceleration needs to be very small. That's not a superscript. That's just, my A. I'm adjusting the size of the A depending on how big that number is. Does that make sense? If I'm pushing this Humvee that's super massive with the same force that I was pushing a shopping cart, then my acceleration is going to be very, very, very small. We cool with that? Let's do some example problems. Okay, let's try this one. So I want to look more at the units. The measurement of newtons is actually, I can break those units down into kilogram meters per second squared, which actually makes perfect sense because this is F equals ma. We good? This is a measurement of m, this is a measurement of a, so your units of newtons is actually known as kilogram meters per second squared. There will be a time when you have to switch back and forth between those two. All right. Here's another symbol that you might see. And it looks like this. Have you ever seen that thing before? You've seen it before? Do you know what it is? It's called the summation symbol. And it basically just means add up everything. We cool? So if I'm going to have two different equations later on, and it's going to look like this. Sum of the forces in the x direction is equal to mass times acceleration in the x direction. And also sum of the forces in the y direction is equal to mass times acceleration in the y direction. This is taking this equation and applying it to two different directions, like we've done in the past. All this is saying is find all of the forces that are going in the x direction and add them all up. And same with this one. Find all the forces that are going in the y direction and add them all up. Are we cool? All right. So let's try to apply this concept to other problems. Let's apply this stuff. Okay, let's see. 3 people can push a 752 kilogram boat. So I've got my boat. And the mass of the boat is 752 kilograms. And they each exert a force of 80.5 newtons parallel to the dock. So, and they each exert a force in the same direction. So I've got 3 different people exerting a force of 80.5 kilonewtons or newtons? Newtons. So, all right. What we want to find is what is the acceleration? A equals what? All right. So which equation are we going to use? Well, luckily for us, there is no choosing which equation to use. We use the same equation. It's sum of the forces is equal to mass times acceleration. We cool? Now, this left-hand side says to add up all of the forces. I'm going to label these forces as F1, F2, and F3. So this left-hand side of this equation right here says to take, well, all the forces that I see. All the forces that I see is force 1 plus force 2 plus force 3. That's a force, and that's a force. Are we cool? Actually, I forgot to do the ever important thing of making sure I have a coordinate system, and that's important in all of the physics that we've done. So this is the positive x direction and positive y direction. We don't really need a y direction because nothing's going in the y direction, but we definitely need a positive x direction. Are we cool? And that's equal to the mass of the boat times the acceleration of the boat. All right, what's the acceleration? That's pretty simple to solve for. I just got to get rid of this thing. Are we cool? So I just add up 80.5 plus 80.5 plus 80.5 divided by 752. Oh, this is in kilograms, and this is in, oh no, this is in kilograms, and this is in newtons. And that's going to give me, plug that into my calculator, and I end up getting 0.321. Are we cool? Do the units work out? I don't know. Yes, no. What's your thoughts? Do the units work? Well, newtons is actually known as kilogram meters per second squared, right? And this is divided by kilograms over here. So I've got kilograms canceling out with kilograms, and I'm left with meters per second squared. So the units I'm supposed to have on this is meters per second squared, which is a good thing because we were measuring A. Are we cool? All right. So let's do this problem now. what if I have the same three people pushing the boats, but this time force 1 is going to be pushing the boat in the positive x direction, but force 2 and force 3, those idiots are pushing it in the negative x direction. Got it? What is the acceleration of the boat? Okay, well, sum of the forces is equal to mass times acceleration. I've got F1 minus F2 minus F3. Do you understand why I have minus? Because they're pushing in the negative x direction. And since I set up by convention that everything going to the right being positive, then the forces that they're pushing is negative. This is just the process of me summing up all of these things. All right. So I really just tack on a minus there, and I plug it into my calculator, and I end up getting negative 1 or negative 0.107 meters per second squared. Does it make sense that my acceleration is a negative number? Yeah, of course. It just means that your boat is actually not accelerating in that direction, it's accelerating in that direction. It's because you've got two idiots pushing against this one person trying to push the boat forward. You've got two people pushing it backwards. So your overall acceleration is going to be negative. And then when you look at this, it also makes sense that this is a smaller number than what I had previously. Because previously I had them all aligning, working together, and it pushes it at 0.3 meters per second squared. But in this case, I've got this guy and this guy basically cancel each other out. And then so it's almost equivalent to having one person pushing this way with a force of 80.5 kilonewtons. It's not going to push it as fast. It's not going to, I don't want to say as fast, because acceleration isn't a measure of speed, but it's going to push it with a smaller acceleration, that's for sure. Are we cool with that? All right, let's do this one. I can throw a baseball, and I can throw a baseball at 90 miles per hour. 90 miles per hour. And I want to, and the mass of the baseball, so this is V final. The mass of the baseball is 0.15 kilograms. Cool? What is the force that I exerted on the ball? Oh, and also, I guess the question is, how far, well, here, let me draw the picture for you. Here's a picture of Mr. Dalday being a pitcher, like Pitcher. Actually, this is the same spelling. So here's a picture of Mr. Dalday throwing a ball. And so throughout this motion, I exert a force on it. And the question that we're trying to figure out is, how big is that force? So one of the things we would need is force is equal to mass times acceleration. We don't have an acceleration. I didn't give it to you, but I did give you a mass. Check. So if we wanted to find a force, we would need to find the acceleration. Are we cool with that? All right. Is there any way I could figure out what the acceleration is if I knew, say, the velocity final, the velocity initial, and let's say delta x, the distance I pushed this ball through? Sure. What is the V final? The V final is 90 miles per hour, which is actually about equal to 40 meters per second. Do you mind if I don't go through that conversion? 90 miles per hour to 40 meters per second? You know how to do that. That's a chemistry thing and even a physics thing. We've done that before. What is the velocity initial? 0. Very good. I started the ball. I didn't have any speed on the ball before I threw it. When I had it back here, it was 0, and then I accelerated it. Here's my question for you now is, what is the delta x? If you don't know, say IDK. Oh, well, I didn't actually tell you the delta x, but we can estimate it for a reasonable person. I would say that the delta x might be maybe my arm's length times 2, right? Twice my arm's length. In fact, it's common knowledge that your hand span like that is how tall you are. And on a good day, let's estimate me to be 2 meters tall. Cool? Or at least say that if I were an average-sized baseball player, I'd be 2 meters tall. If I'm an average-sized Filipino, I'm not 2 meters tall. So with all of this in mind, we can figure out what A is. V final squared equals V initial squared plus 2A delta x. I'm going to solve for A. This is 0. So V final squared equals over 2 delta x is equal to A. So I simply plug my numbers into this equation and I end up getting 400 meters per second squared. So then I multiplied that times my m to get my force. Force is equal to ma, which is 0.15 kilograms times 400 meters per second squared, and I end up getting a force of 60 newtons, which if you convert that to pounds, it's about 10 pounds. So in order to throw a 90-mile-an-hour fastball, all you got to do is exert a force of 10 pounds on a baseball over the course of your arm span. That's easy enough. Why doesn't everyone throw 90-mile-an-hour fastballs? To be honest with you, I can't throw a 10-mile-an-hour fastball. I don't even know how to begin to throw a fastball, but I'm just saying. You just need 10 pounds of force throughout the whole thing. Are we cool with that? So I guess the point of that second problem is this. Is that, yes, all you need for this entire chapter is F equals ma. Does that mean I throw out everything that I learned previously out the window because, I don't really, I hated it? I don't care about the delta x equals v naught t plus 1/2 at squared, or the v final squared equals v naught squared plus 2a delta x. No, we're still going to use that stuff. That still is useful. It's just we're applying it to F equals ma. So I might ask you some creative ways to calculate a, and that would be the way to do it. Are we cool? All right, I'm going to wrap up class. That was pretty good for an introduction. How do you feel about F equals ma? Is it familiar? Does it make sense to you? Is it easy? Hard? All right, cool. I feel like this chapter is going to be pretty cake. Vectors. This has a lot to do with sine, cosine, and tangent. So make sure you guys brush up on that. All right. make sure you read the chapter on this stuff. I'll post it up today. I know my class looks pretty sparse, and it's because I haven't posted my lessons to it yet, but I will. All right, talk to you later. Goodbye.